Hello dear students, welcome to Pen and Paper Chemistry on YouTube. Hello dear students, Thermodynamics part 11, and we are extending the concept of Hess's law in terms of what we call as the Born-Haber cycle. This was given by two German scientists, Max Born and Fritz Haber, in order to deal with the energetics or the energy associated with a chemical reaction or with a chemical process. So this is nothing but an extension, as we said, of Hess's law. What is Hess's law? Whether a process takes place in one step or a number of small steps, the enthalpy change remains the same. You have to remember this. Before we go on to the Born-Haber cycle, please remember it is very easy. You will go step by step, and once we finish it, promise, you will feel very comfortable with it, because that was my situation before I started actually recording this video. Before we go on to the equations, there are certain terms that I would like to introduce over here. Enthalpy of sublimation. Let's break it up. Sublimation, the process of direct change of a solid into the gaseous form. Enthalpy of sublimation, the enthalpy change when 1 mole of a solid changes into 1 mole of a gaseous substance. Ionization enthalpy. So first, ionization. What is ionization? When a neutral gaseous atom loses an electron, the process is called ionization. Ionization enthalpy. The enthalpy change when a neutral gaseous atom loses an electron. Molar ionization enthalpy. When 1 mole of a neutral gaseous atom loses an electron, the enthalpy change taking place is called as the molar ionization enthalpy. Electron gain enthalpy. So let's break it up again. Electron gain, the process when an electron is added to a neutral gaseous atom. The enthalpy change taking place in this process is called as the electron gain enthalpy. And if I'm talking about 1 mole of the substance, then it is molar electron gain enthalpy. That means when 1 mole of neutral gaseous atom gains an electron, the enthalpy change taking place in such a process is called as the molar electron gain enthalpy. Lattice enthalpy. Now this is quite confusing at times, and we shall be talking about this again in our part 12. But we need to understand the basics of this in order to go ahead with the second leg of this lesson. Lattice enthalpy. First, you need to understand the term lattice. Lattice is nothing but three-dimensional ordered arrangement of particles. This is what we call as a lattice. So when you talk about sodium chloride, it's not just one sodium ion and one chloride ion. No, it is a number of sodium ions surrounded by chloride ion, and each chloride ion in turn surrounded by sodium ions on all sides. It's not just 2 dimensions, it's above this board, inside this board. So a regular 3-dimensional arrangement of particles is what gives us a lattice. In order to form a lattice, some energy has to be lost. As we said earlier, whenever they have to gain something, they have to release something to the universe. It's a give and take relation. So they get an oppositely charged ion close to each other or close to their vicinity. But in turn, they have to lose energy to the universe in order to remain stable, in order to remain happy and satisfied and relaxed. So sodium ion, chloride ions, they come close to each other to form the sodium chloride lattice. Lattice formation, there is attraction. Whenever there is attraction, there is willingness to come together. energy will be released. Hence, this process is exothermic. They'll release out energy. If they don't release out energy, they don't become stable. So we will specifically call it as lattice formation enthalpy. That means when 1 mole of lattice is formed from the respective ions in their gaseous form. Lattice dissociation. So in order to break this lattice, in order to break this bond or friendship between two oppositely charged ions, what will you have to do? Yes, you will have to give energy. In other words, this will be an endothermic process. You need lot of tactics in order to get these oppositely charged ions away from each other. Hence, lattice dissociation enthalpy is the amount of energy, or the enthalpy change to be more specific, when 1 mole of a solid breaks down into its respective ions so that they are infinite distance apart from each other and in gaseous form. The two values numerically are the same. They just indicate how much of energy is associated with a particular crystal or an ionic substance. It's just that their signs are different. If one is positive, the other is negative. Now, out of all the terms that we'll be using over here, there's something called as bond dissociation enthalpy, which I have not discussed over here. Just to give you an overview of bond dissociation, that means when bond is broken between two atoms in their standard state is what we call as bond enthalpy. We shall be talking about this particular concept again in part 12 of our video, because we need to discuss it in more detail, as it decides or is a deciding factor in the behavior of many molecules. That is why we shall be discussing it in more detail in part 12 of this video. Now, after having introduced these terms, I would request you to pause the video, absorb these definitions, and then go on to the right half of this. Coming to the Born-Haber cycle. Born-Haber cycle, as we said, is nothing but an extension of Hess's law. So I'm taking a simple example which you will find in most of the textbooks as well. Sodium solid combining with chlorine atom to give you sodium chloride solid. Now this chlorine atom is not as an atom, it is existing as a chlorine gaseous molecule, which is the most stable form of chlorine. What is standard molar enthalpy of formation? Standard molar enthalpy of formation is when 1 mole of the substance is formed from its elements in their most stable state under standard conditions. I want to find out this. How do we go ahead? Now, according to Hess's law, Born-Haber said whether you carry out the process in one step or in a number of steps, the enthalpy change has to be the same. Okay? Agreed? So they extended this concept in order to give us this specific cycle. So sodium solid changes to sodium gas. It's a process of sublimation, molar enthalpy of sublimation, which is 108. Now if you notice over here, I have not put the units. Why? Because in order to simplify the process, I've done the steps on the left hand side. The molar enthalpies are given on the right hand side. We've just put in the numerical values. All are in kilojoule per mole. A positive value indicating an endothermic process, a negative value indicating an exothermic process. Sublimation requires energy. So molar enthalpy of sublimation for sodium is 108. Ionization. The sodium gaseous atom undergoes ionization to form a sodium ion in the gaseous form. Molar enthalpy of ionization 495, because it will need energy to take away the electron from it. So it's an endothermic process. Bond dissociation enthalpy. That means the chlorine molecule breaks down to form two chlorine atoms. We are breaking the friendship between two chlorine atoms which had come together to form a friendship, a bond. The bond enthalpy for this is 242. That means this much of bond energy is or enthalpy is required in order to break the bond between two chlorine atoms. Electron gain enthalpy for chlorine is negative 342. Again, because there is attraction between the protons of the chlorine atom and the electrons which it has acquired. So give and take, it is getting an electron. In order to be stable, it loses out energy so that it can be stable. So it's an exothermic process. Sodium ions, gaseous form, chloride ions, gaseous form, come together to give us sodium chloride in the solid form, resulting in what we call as a lattice. The enthalpy change taking place is known as the lattice enthalpy, more specifically the lattice formation enthalpy, and this is negative 788 kilojoule per mole. Please remember all these values are in kilojoule per mole. It's only for the sake of simplicity that I have not written down kilojoule per mole everywhere. Now, von Haber said, okay, whether you talk about the summation of all of these or only this value, they are the same. Agreed. So equation 1, equation 3, equation 5. Sodium solid, yes, we want sodium solid. But do we want sodium gaseous atom over here? When I'm taking equation 1, I'm getting sodium in the gaseous form as a bonus. I don't want it. That's not what we want over here. So we need to take equation 2 as well, because what is a product over here is a reactant in the second equation. So when I add them up, they get nullified. Now, again, chlorine. If you notice the top equation, that's my target equation for which I have to find out the enthalpy change. It's just half chlorine. Whereas equation 3 is giving me Cl2. So what do I do to get half chlorine? Yes, we multiply equation number 3 by 1 by 2. Now, in the process, I'm getting a chlorine gaseous atom as a bonus. It's coming on the right hand side. Do I need it? No. So, what do we do? In order to nullify, we'll take equation 4 as well. So, what is the product in equation 3 would be a reactant in equation 4. Nullified. Now, we are left with chloride gaseous. Adding equation number 1, 2, 4, 5 and half of equation number 3. That's what we do in order to get the molar enthalpy, standard molar enthalpy of formation of sodium chloride. Put in the values 108, 495, half of 242, negative 342, negative 788. Pause the video. Do the calculations. Let us see if our answers tally. Yes, the value comes out as negative 413 kilojoule per mole. In other words, the formation of sodium chloride is an exothermic process. Now, what is the benefit of this if it's just an extension of Hess's law? Now, it's very easy to find out the standard molar enthalpy of formation of compounds, but it is a bit difficult to find out their lattice enthalpy of formation or lattice enthalpy of dissociation. Or you could talk about the molar enthalpy of sublimation or ionization enthalpy. So if we know the other values, so if you notice 1, 2, 3, 4, 5 set of steps that we have taken over here. If out of these, and the sixth one we had determined, if out of these 6, if we know any 5 by other methods, we can determine the 6th value by using the concept of the Born-Haber cycle. good if you practice a few numericals based on this concept, or firsthand, just write these steps yourself in order to get a firm grasp on this particular concept. In part 12, we shall be talking about the bond dissociation enthalpy, the solvation energy, the hydration energy, and again extend the lattice energy concept further. The only mission of this channel is to make learning chemistry easy and fun for all you students, with the help of the periodic table, the flowcharts, the graphs, diagrams, dealing with numericals, how to deal with numericals, and this can only happen when you keep a pen and notebook ready so that you can also take down notes for offline reference. There is no subscription to join the channel, there is no payment at all. Only request is to help spread a word about the channel by sharing it with friends, classmates, juniors, seniors, so that chemistry can be easy and fun for one and all. See you in the next video.